This is a mark scheme for your task book, Biochemistry and Cell Organisation, and particularly enzyme question 7. So, oh dear, graphs and enzymes, oh dear. Right, can we identify any bits of this blurb to start with? I'm going to think, can I find my enzyme, my product, my substrate, that sort of thing? Amylase, A's, that's going to be our enzyme. Catalyzes the breakdown of starch, that's our substrate, and this is our product. So our substrate is turning into the products, and the enzyme is catalyzing that. Okay? And we are using equal volumes of our starch and enzyme, and here we go, 2 temperatures, 25 and 37, so one's higher than the other. And how are we judging this experiment? The quantity of maltose produced was measured and plotted. Okay, so as time increases, we're measuring the mass of maltose, which is our product. So at the start, we haven't got any product. So at the start of the reaction, it's all starch. At the end, it's all maltose. So no product at the start. It's all substrate, and then over the course of the reaction, the substrate is turning into product until finally it's all product and there's no substrate left. And the different temperatures this happens slightly differently. Okay? So use your knowledge, so that's your revision and things in your notes, of enzymes to explain the differences between the two graphs. Okay? I'm going to talk about why this 37 degrees you get more mass of product formed per unit time than our cooler temperature. So higher temperature, we're going to get higher kinetic energy. Okay, that's a good starting point. I've got 4 points to make here, and I've got 5 lines, so I'm probably hoping I can put a point on a line and then maybe a spare point in case I didn't say one of these quite right. So higher kinetic energy. We're not going to say KE or anything like that, we're going to say our full kinetic energy. If things are moving around faster, there's going to be more chance of a collision between our active site and our substrate. So more chance of a collision between active site and the substrate. And so we're going to get more enzyme substrate complexes. So more enzyme substrate complexes, or substrate enzyme complexes, doesn't matter which way you say that. And so we're going to get our starch converted into maltose faster. So faster or more starch converted to maltose at this higher temperature. We get to the end point of the experiment quicker. So all the product made faster. And possibly we could mention, we've said it there really, but even at the slower temperature, the total mass of product is the same at the end. So it happens eventually, just slower. So but even at 25 degrees C, all the product eventually made. Okay, so 4 marks there. Hopefully we've got it in our first set of answers. On the graph below, draw a line to show the rate of reaction for the enzyme at 37 degrees. OMG. What are we going to do here? No idea. Just miss that and carry on. No, you need to do this. So rate of reaction, which is how fast it's happening per unit time. Good, right. So we've got time on the bottom, nothing up the side. It says draw a line. We could put some numbers on here, but it's probably overkill. Right, so we're going to draw a line, 2 marks. There'll probably be 2 areas of this line that they want you to get right. So, what's the rate? Well, let's have a look at the first bit of the experiment and see if we can work out what the rate is. Which line is it again? 37. 37, so it's this line up here. So, what's our rate? Well, our rate's actually the same, because this line is straight. It's like a distance time line. So the speed or rate is the same up to just past 6 minutes. So whatever we're going to draw on here is going to be the same rate up until 6 minutes. And then after that, this total mass levels off. So if we're not getting any more product formed, how fast is it working? So if there's no substrate turning into product, how fast is the reaction working? Well, it's slowed down to a halt, so it's going to be 0. So we've got a fast rate here, then it slows down, and then more products we make, so it goes down to 0. So on here, I'm going to call this 0.5 there, and 2, 6, get there so you can see it, and kind of up to about 6. The rate's going to be the same, and then after 6, then we don't get any more product formed. So it's going to go down. At which point is the rate going to be 0? Well, after 8, that's just a straight line. So probably just between 7 and 8, that's when it goes down to 0. So between 7 and 8 there. So I'm just kind of nosedive that down there. Maybe a bit more on the curve than I've drawn. And you're kind of going to get 1 mark for this kind of reverse version of this, and 1 mark for this going down between 7 and 8, where it levels off. So, a bit of a stinker, that question. Now this should be a little bit more easy. State one other factor that could have affected the rate of reaction of the enzyme at 37. This is better. This is wanting, can I have another controlled variable? So what are we investigating here? We're investigating temperature, and so the easiest thing to say is, well, if we're investigating temperature, I'm going to keep the pH the same. Other things that we could keep the same are, well, here's our substrate, starch. Would it be fair if we started off with different concentrations or volumes of starch in an experiment? No, so we need to keep that the same as well. And would it be fair if with one experiment we had a small concentration of enzyme, or another one with a larger volume or concentration of enzyme? No, it wouldn't be fair. So things that we're going to say here are pH, substrate concentration, or enzyme concentration. And so I'll go for pH there, because I'm quite lazy and I don't want to write those other ones down. Then you think, moving on to the next question, but oh no, There's more on this enzyme question, yikes, and there's a whole big paragraph to read. Biological washing, so there's our enzyme there, okay, and I'm looking for substrates and products and things like that, blah blah blah. Milk protein, okay, being digested. So this milk protein, that's our substrate, and it's being digested. It doesn't tell us what it's being digested into, but where it has, we get this clear area. So we've got washing powders in here. So there's the enzyme 1, enzyme 2, enzyme 3, enzyme 4. This whole thing is milk. So it started off all of this all being the same kind of greyish colour. And then over time we get this clear area forming where the milk has disappeared. It's being digested into something else. Okay, and that was over a day at a certain temperature. Okay, I think we know what's going on now. Which is the most effective powder at digesting milk protein? You'd probably guess the right one here. So which one has the milk turned into the products? It's just testing, do you actually realise which one has been digested the most, or it's turning the milk protein into the product? And that's number 1. It's got the biggest clear area. So it says state, so I'm just going to state it. I'm not going to give any reasons there. Explain fully why manufacturers of biological washing powders recommend that these powders are not used at high temperatures. Right, okay, I could just make some stuff up here, or I could go, right, is this a question about temperature? High temperatures. What would possibly happen at high temperatures? You go, okay, I know this. This is all about denaturing and so on. Okay, well, 3 marks. So there's my 3 marks. I might even say another thing there, just in case I say one of my 3 things wrong. So let's talk about what happens. So they might denature. So denaturing might happen. And let's just go, right, well that's my headline. How do I give more details there? So things like what is denaturing? So that's the active site changing shape, so the substrate doesn't fit, substrate can't bind because they change the shape, or no enzyme, can't spell enzyme now, substrate complexes form, that sort of thing. And then, well, why does that happen? Why does this all happen? So it's more energy, so again you get more vibrations, molecules, you get hydrogen bonds broken in that protein tertiary structure, and in there those will all get your marks. So it's just going, I've identified this question is about high temperature, and I'm going to talk about stuff from my notes. I'm not going to make anything up. I could possibly make something up for this because it says suggest, but I'm going to try and keep an eye on what I know. 2 marks. Suggest why it would be incorrect for a manufacturer to claim that the powder is the best biological washing powder. What do you use washing powder for? Well, if you play football, they've got grass stains from chlorophyll. If you're as mucky as I am, eating hot dogs and burgers, you get ketchup down you and all sorts of stuff. So the only thing that this is testing is milk. Then we've got any evidence at all that it's any good at other stains like ketchup, proteins or carbohydrates, things like that. So my first suggestion is, what about other things apart from milk? So this experiment only about milk. Yeah. E.g. things like fats, carbohydrates, things like that, not tested. And people need to get rid of these stains as well. And actually, well, are there some other washing powders that weren't tested here? We don't know. So only 4 powders tested here. So there's 2 points there. And then, thank goodness, we're at the end of this question, and we can do it again next time. Well done for getting to the end of that.